Benoit Sirois from HES in France, and we'll be telling us about his work on the Navigator function and the ON archipelago. Welcome, Benoit.
Thank you. It's very nice to be here and have the opportunity to talk about what's been occupying the first 2 years of my PhD at HES. And it's also nice to be back in Montreal after a couple of years of absence. Today, I'll talk about this Navigator function that we've been working on. What I'll talk about, you can find in these two papers. The first paper where we came up with this Navigator function was a big collaborative effort with the group of my supervisors, Navarishkov, which included Martin Rehorst at the time, some other people in Paris, Wald van Ries at École Polytechnique in Paris, and David Simmons-Duffin in Caltech, and Ning Su in Pisa. And then, well, in this work to show what this Navigator method could do, we used as a test model the 3D easing model. And in this more recent paper, I played around with the, well, I played around with the ON models in d dimensions and tried to use them to show what this Navigator method can do. So the outline of the talk is the following. I'll try to give a very brief introduction into what is the numerical conformal bootstrap for those that don't know. And then I'll present the Navigator function and show what it looks like and what it enables us to do in these two simple examples of the easing model and the ON models. So, okay, before starting, I thought I would put up a picture. If you've ever attended a conformal bootstrap talk, you've certainly heard nautically related terms, archipelagos, islands, and so on. And if a bootstrapper sees himself as some sort of explorer, the landscape of CFT data, then it's only natural that he would want some way to orient himself in his search. And this is what the Navigator method should. Hopefully, I'll convince you that this is what the Navigator method helps us to do. So in the numerical conformal bootstrap, we try to use conformal symmetry and general self-consistency conditions to constrain the possible values of CFT data. In the most basic example, if we have a CFT without any particular global symmetry, and it has some scalar operator phi in its spectrum, then we can take its 4-point function, impose crossing symmetry, where we can exchange any two xi's between each other, and it doesn't change the 4-point function. And the OPE, which says that any two operator insertions is equivalent to an infinite sum of a single operator insertions, to turn this 4-point function into a sum rule, where in the sum rule, the f function is completely known. And so we can use this to solve for the unknowns, which are the OP coefficients, the lambdas, and the spectrum of the theory, which is the spectrum of scaling dimensions and of spins of the operators of the theory. And what we'll do is assume, make some assumptions about what operators we find in this OP and check whether we can solve this crossing equation. And if we scan over assumptions, we're going to get some exclusion plots where some points will be allowed by crossing and some points won't. Maybe the most famous plots in the numerical conformal bootstrap is this one, where instead of looking at a generic CFT, we studied, well, these people studied a Z2 invariant CFT and looked at all 4-point functions, including the lowest dimensional Z2 odd scalar, which is sigma, Z2 even scalar, which is epsilon. And if you impose crossing on these sets of 4-point functions, you get a plot that looks like this, where for a given precision of the numerical conformal bootstrap setup, you get a small island and a big peninsula to the right. And if you push the precision higher, this big peninsula will be pushed further and further to the right, and the island will converge into the known critical exponents of the 3D easing model. And so this is all well and good. Then why should we need some other method if the conformal bootstrap seems to work so well? Well, the 3D easing model is, in some sense, the simplest CFT we can look at. In general, if we look, for example, even for scalar CFTs, at CFTs with more complicated global symmetry groups. Sorry, was there a question? Okay. This is usually going to complicate things. We saw that last week in Shai Chester's talk. If we want to isolate a theory either in an island or at the tip of some allowed region, then we're going to usually need more correlators or more assumptions. And this is usually going to mean searching in a larger dimensional space. For the easing case, we only had to look at 2 operator dimensions, and this was enough to isolate the easing model. But sometimes you're going to need to look at tens or more operator dimensions or OP coefficients in order to really isolate your theory. And then scanning over each point in this 10-dimensional space is not going to be very efficient. And also, for the easing model, we know critical exponents very well, so we know where to look for in our space. I think people have resummed the epsilon expansion to 8 or 7 or 8 loop orders for some critical exponents. But in general, we don't really have as good control as to where to look in our parameter space to find our theory. And so we would like to have a method where we could start from a rough, have a rough idea of where we need to look and guarantee that we would converge to the theory we're looking for. And so the idea is the following. Well, let's say I was doing a scan, as I've mentioned before, then at each point that I scan, I can determine if the point is allowed or disallowed, and I can construct some sort of indicator function, which is, I could say an allowed point is going to have the value -1, and a disallowed point is going to have the value 1. But I can't do anything with this function, because if I know that the point x has value 1, this doesn't tell me anything about its neighborhood. The point right next to it could have -1, and there's no local information. So what we would like to do is replace this this indicator function with some continuous function, which would be positive in regions of CFT data space where we cannot satisfy crossing, and negative where we can. And well, if we believe that our bootstrap setup is constraining enough that it should isolate the theory in some small island, then to get to that island, all that we would have to do is minimize the navigator function. So this, well, this goes into the benefits of the navigator method. It gives us some amount of local information to orient our search. So if the navigator function is very large, then we know we need to take a big step to go into the allowed region. If we want to go into allowed regions, we can minimize the navigator function, and well, any good minimization algorithm is going to scale much better with this dimensionality of the search space than a rough scan over every point. And if the island we're looking for, well, the island we're looking for should have some basis of attraction around it, such that if we start in some rough vicinity, this minimization algorithm should lead us in the allowed region. So really, yeah, we would only need rough starting points in our search to converge to the island. And the last benefit is that we're often going to be interested in families of CFT. Put some there. Well, Q-state POTS model we talked about last week. It could be the ON models or the d-dimensional easing models. And the navigator function should help us flow also in this space of external parameters. If we've found the minimum of the navigator function for some value p, then we can then we know how this minimum. Well, we know that this minimum, the variation of this minimum with respect to the external parameter is just going to be a function of derivatives of the navigator function at the minimum we know. This is just this takes maybe 2 or 3 lines to demonstrate. So if we've managed to go to one minimum and we change the value of our external parameters, we should be able to use this gradient information to get a good starting point for our search at the next value of the external parameter, and this should help us flow faster in this external parameter space. But we need to have, now that we know that we want a navigator function, we need to be able to construct one. And the construction goes as follows. So on the top equation, I've put the previous crossing equation that we had in the first or second slide. And I've added to it, what I want to do is add to it some term such that the augmented crossing equation, which includes this added term, always has a solution for some value of this lambda parameter greater than 0. And I claim that for some set of assumptions that I put into this variable x, a valid navigator function can be defined as the minimal value of lambda, such that this augmented crossing equation always has a solution. And this is pretty simple to see. Of course, if this minimal value of lambda is greater than 0, then that means there's no solution with lambda equals 0. And so the original crossing equation doesn't have a solution. So we have that, we indeed have that when there's no solution to crossing, the navigator function is positive. And if the minimal value of lambda is below 0, then we can just take a convex combination, a convex linear combination of the solution with this minimal value and of the known solution with this lambda star, which is greater than 0, to obtain a solution with lambda equals 0, which is our original crossing equation. So indeed, when this minimal value of lambda is below 0, we can construct by hand a solution to crossing, and so we've defined a nice navigator function. But we need to find such a term lambda m star such that we always have a solution to the augmented crossing. And in the original paper, we gave two constructions. Maybe the most intuitive one is the one that I give on the board, which I call the GFF navigator function. So we remember that we got the original crossing equation as derived from the 4-point function of 4 identical scalars. Well, one valid CFT 4-point function with 4 identical scalars is the GFF 4-point function, which you get just by Wick contractions. This will exist for any value of the scaling of the operator pi. And we know the spectrum of this CFT 4-point function. It has a spectrum looking like a free field, but with which is only a free field if delta phi is d-2/2. And the term, so we have this known solution to crossing. The term that we're going to want to add to our original crossing equation is that we want to add every operator in this GFF solution that is violated by the assumptions we made. For example, we could have assumed that in the here, maybe I can point it. In the operators that we find in the phi OPE, we say that we want every one of these operators to be above dimension 1.5. Then the term that we would need to add is the only operator in the GFF solution which has dimension below 1.5. So there would be this operator with dimension 2 delta phi. And if we do so, we will always be able to solve the augmented crossing equation because it will always have in it the GFF solution. We have added by hand the operator that violates our assumption, and then all the other operators in the GFF solution will be found in this sum on the left. And so that's it. Of course, now I presented this GFF navigator function in the simple case of one scalar 4-point function, but this generalizes to multiple 4-point functions or to scalar CFTs with global symmetries, where the operators that you'll be looking for in this generalized GFF solution, you'll just assume that every one of them is an independent GFF, and you'll always be able to construct this GFF navigator function. And so this is it for the general construction. Now I can show you what this navigator function looks like. Now here I show you the navigator function for the exact same setup that went into producing the exclusion plot right here. So we're looking at a CFT with global Z2 symmetry, and we'll look at 4-point functions of all 4-point functions of these two lowest lying scalars. And what we see is that we have the navigator function is bounded above by what looks like 1, which is just a normalization, but 1 is an upper bound because the navigator function is always bounded above by the GFF solution. And we see that it dips to close to 0 and maybe a bit below 0 at dimensions maybe 5.518 and 1.41. And if we zoom in on that region and we produce a heat plot, we get the following plot, where the white region is the region where the navigator function is negative. And we see that this region where the navigator function is negative coincides with what we had in the first exclusion plot for the region that was allowed by crossing. So our navigator function reproduces what we get by the usual scanning-based methods. And the nice thing is that here, the black cross is the value inside the island, which has the smallest, for which the navigator function is the smallest. And the green cross is the known value for these dimensions for the Ising model that was obtained at much higher precision. And so for this generally low precision setup, we see that the island is quite large. The minimal value, well, the point where the navigator function is at its minimum is very. The other ones are gonna go to 0 at n equals 1, and then are going to become negative below n equals 1. So these operators will violate unitarity a lot, and you find some of them at low scaling dimensions, and this is what makes the bootstrap solution disappear. This is one example of this operator that we looked at, that the OP disappeared at a square root. And so that's it. Now there are two directions in which one can go. Just think that he or she is interested in this navigator function. Of course, now it would be nice to use it to bootstrap models where there are still nice open questions, the 3Ds and the 3D ON models are pretty well known. But Shai Chester last week talked about the Potts model. In our group, we're working on this ON times OT model, for which there's still open question as to whether the are coming into this symmetry in 3D. Because it's supposed to merge between 4 and 3 dimensions and other. And on the more numerical side, throughout the years, people in the bootstrap community came up with smart ways to make the scanning-based method more efficient. For example, if you're able to determine for a point if this point is allowed or disallowed, you determine that by solving some semi-definite program, and you can kickstart the solving of this semi-definite program at a nearby point by the solution at the point that you just covered. But this doesn't work very well with the navigator function, and so there's still some improvements to be made to have it be competitive with the scanning-based methods, especially at very high precision. And okay, that's all I wanted to say.
Thank you very much. So I will put the microphone.
No, it's working with this laptop. I'm sorry about it.
It's working?
No, unfortunately, all the microphones are off right now.
Okay,
I haven't talked on the laptop. Maybe we should put the laptop on the desk.
Yes, yeah, of course. I didn't want to interrupt the thinking.
Okay, so we have time for some questions. Any questions, William? Yeah.
Other than anyone else. Okay. So do you have the same plot with the islands, the oil model, and the cross, and then over the minimum?
No, I don't have them. I don't believe we've made these plots, in part because what we want to do is go away from having to produce the whole island in order to study our model. What's nice about the navigator function is that if you're more cavalier and you know that there's an island, then you can just go to the minimal value of the navigator function, which is going to be inside the island, and just follow this. So you don't always have to plot the whole thing.
No, you use the known island as your minimum.
Ah, yes, I didn't do that. No, for this, in part also because I didn't push it to very high precision, but surely I could do that. I just don't have it. But I think they are closer to the known values than in generic ones. I do, because the UN islands are a bit more spread out than the Eastern islands, but the values that we get in instance are they compare favorably to the numbers.
I have like question about bootstrap, not so much about
Sure.
the navigator work, but for these ON workloads where you talk models.
Uh-huh.
So I was just wondering because I've noticed that there hasn't been any new result that I know of since I think 2016, 2018.
Yeah.
Well, just to say that briefly,
Sure.
there seems to be decent agreement with, let's say, FRG, expansion, Conformal for the data exponents.
Okay.
So for like unit inverse, for the inverse exponent, it seems to be like the expansion, RG, and the Conformal seems to roughly agree, and the bootstrap is kind of pretty different. So I was wondering if you had any comments about
Well,
this.
I put this in there because I do know that I think it's David Poland's group is working on this exact model, and I think he's attending the conference, so maybe he'll have a better answer than I do. But I think they had pretty promising results for this model that we're showing at a conference. Yeah.
Back in Navigator, you showed this M star the blocks of the generally free fields. Is there a better choice, or does that depend on if you're studying?
I guess if there's no general construction of how one should go to put this M star. In our paper, we gave one other example, which was just sum up enough operator. So these crossing equations, what we do numerically is that we transform them into some, we expand these crossing equations depend on some cross ratios U and V, and we expand the crossing equations around some point, and we get a set of vectorial. The crossing equation becomes a vectorial equation, and if you just in this lambda M star, if you just sum up enough operator, basically just from the linear dependence of if you sum enough operators that they become whether that they are that they reproduce the whole space of the this if your bootstrap equation is a vectorial equation with n components, you just sum up more than n vectors, and by linear dependence you're going to get that this always has some solution, and so you can I don't know if that's a smarter way or a dumber way to do it, but you just have to be ingenious enough to find some term which is going to give you a solution to crossing always, and this seemed like the most logical, but surely you could think of it. This one, the GFF navigator is more useful because you have more control on it. You know, for example, that it's going to asymptote to the value that's given by the GFF solution. For this other construction I mentioned, I don't think you know what it asymptotes to. So because we know the asymptote, well, obviously a minimization algorithm usually requires, it's nicer to have a convex function. This function asymptotes to constant value. So if you start very far, then most likely you're not going to converge to the island because you're going to jump over it and never see it. But because you know what it asymptotes to, you can transform it in a nice way where, well, you map this asymptote to infinity, and then the minimization algorithm works better. If you don't know what it asymptotes to, then and you start very far, then maybe its behavior very far is not a good indicator of how it's going to behave around the point that you want to get to, and maybe you're going to jump over it.